In the previous video, we explained what the derivative of a regular expression is using Pac-Man. In this video, we're going to use ragas from Indian classical music to explain how to extend derivatives with new operators, simplification rules, and memoization as an optimization strategy. We will call them regular expressions, or ragaks for short. A raga is a melodic framework for improvisation in Indian classical music. Here's an example of someone playing a raga. Notice how the player slides their hand up and down the strings. There are very strict rules that decide what notes they are allowed to play next. Ragas are basically the Indian version of Western scales. They're stricter than Western scales though, since the next possible note is simply not chosen from a set, but rather depends on the current note. Also, notes are labeled a bit differently. They're labeled relative to the start note. Here you can see how they're labeled relative to C, but if we started at D, then D would be labeled as S. There's a lot of other very interesting things to cover about ragas, but I will skip over microtones and all the other theory, since we're only interested in the stricter rules for this video. As an example to compare raga with later, let's look at how we would describe a Western scale using a regex. In this case, the C major pentatonic scale. We can check if it matches the sequence of notes C, E, G by using the derivative algorithm we discussed in the previous video. First, we take the derivative of the whole expression with respect to C. If we strictly follow the rules, we see that C matches the first C, and it becomes the empty string, concatenated with the star expression. Now we can take the derivative of this expression with respect to E. If we do that, it expands to this pretty large expression. But this is just what the concat rule expands to. And you feel free to go and double check my work, but I don't want to bore you with the details. The important thing I want to demonstrate is that everything in the previous video went a bit too smoothly because I was cheating and applying simplification rules on the fly. This is what happens when I don't do that. Things quickly get out of hand. Luckily, we have lots of simplification rules that can help. I'm going to go line by line here and explain what these simplification rules are. First one shows that when we concatenate an empty string with another expression, we can throw the empty string away. Same goes for the right side. On the next line, we show when we OR with the empty set, we can throw the empty set away. Also, if we have two expressions that are the same and we're ORing them with each other, we can throw one of them away. If we reorder expressions in OR, we can try to increase the likelihood that we have duplicates. When we concatenate with the empty set, the whole expression becomes the empty set. 0 or more times is just 0 or more. 0 or more empty strings is just the empty string. And this one's a bit tricky, but 0 or more empty sets, if you don't have any empty sets, just 0 of them, then that's just the empty string. And I'm sure you can think of more, but let's go back to our example and see how we can apply some of these. Now, let's continue our example where we left off with our very large expression and apply some simplification rules. We see that we're concatenating the empty set with another expression, which we can simplify to the empty set. And now we can throw away the empty set on the left side of the OR. Next, we can throw away all the empty sets in this big OR, and then we're left with the empty string concatenated with the 0 or more expression. And this is exactly the expression we got when we took the derivative with respect to C. So we've come like full circle. But actually we can throw away the empty string since it is part of a concatenation, and we simply get this fully simplified 0 or more expression. Now we can take the derivative with respect to the next input character, G, and after simplification we also get the star expression. And this final expression matches the empty string, which means that the sequence CEG matches the C major pentatonic scale. There are two ways we can apply the simplification rules. We can apply them after each derivative step, or we can use smart constructors. Smart constructors are just constructors with some logic. And in this case, the logic that we're going to have inside our constructor is the simplification rules. This means that when you try to create an OR between an empty set and another expression, we will simply return the other expression. This way, it is impossible to construct a regular expression that is not simplified, which also means that we don't have to check that each expression is simplified after we have calculated the derivative, which saves a lot of double work. Our smart constructor can also calculate a hash to make comparisons that are required during simplification faster, and in general, this is the preferred way of implementing the algorithm as it is much more efficient. Another thing we can do to optimize is to use memoization. Memoization is just a way of remembering or memorizing the results of a function so we don't have to go and recalculate the same result, given we have seen the inputs before. This only applies to pure functions that always return the same results given the same inputs, which is perfect for our use case. We can start saving the results of the derivative function in a little table. For example, given the expression that must start with a c, we go to the star expression given the derivative is taken with respect to c, as you can see in row 2, column 2 of this table. If we run through our other derivatives, we get a total of 3 cells filled in. The rest of the table will be filled in as we calculate more derivatives, and we can also use this table to look up results that have been calculated before as we calculate new derivatives given the algorithm is recursive. If we do fill in the table completely, we get what is called a transition table for the Deterministic Finite Automata, or DFA. Here you can see the resulting automata or state machine. Each state is represented by a regular expression, and the nullable function represents the accepting function of the DFA. I just think it's so cool that we get this for free. We lazily build a transition table using our memoization strategy, and our simplification rules can be used for minimization of the state space. Now back to Ragas. Here is a type of pentatonic scale called Raag Bhupali. Given the current note, you must choose the next ascending or descending note. For example, given G, you can choose P if you want to ascend, or R if you want to descend. This is much stricter than a Western scale where you can choose any note in the set at any time. The problem is describing these Raga sequences requires a new operator. And this means we need to extend our algorithm to handle more operators. To describe Raag Bhupali, we need recursive regular expressions or context-free grammars. This means we need to add references or links to our regular expressions. Here is a context-free grammar that describes Raag Bhupali. Our first note S is followed by its ascending or descending note, and the whole expression is then repeated 0 more times. The ascending note R itself is ascended by G or descended back to S, which is represented by the empty string, because when the expression R ends, the bigger expression S can start again. Same goes for the rest. G is followed by P or R, P is followed by D or G, and D is followed by P or a termination since it is followed by S. To get this linking feature, we need to extend our derivative algorithm to include a new operator for references. To extend derivatives, we simply need to implement the nullable and derivative function for each operator. For example, here's what it would look like for the AND operator. You can see the logical operators can just push the problem down. This is why it's also very easy to implement the NOT operator, because it can also just push the problem down. Okay, that was too easy. Let's try to invent an operator called interleave or shuffle. We want to interleave two expressions, S concatenated with R and D concatenated with G. This would result in the following sequences being accepted. S is always followed by R and D is always followed by G, but otherwise the 4 nodes can interleave in any order. We could easily extend our regular expression matcher to handle this operator by simply implementing the derive and nullable functions for the interleave operator. So we have to think, what is the expression that is left to match after matching a single character of the interleave expression. Well, we are either going to take the character from the first expression or the second expression. So we can take the derivative of the first expression r and interleave it with the second expression, or we can take the derivative of the second expression s and interleave it with the first expression. Easier than expected, and it works. For an interleave expression to match the empty string, it can only happen if they both match the empty string. And that's it. Very complicated operator implemented very simply. But we were here to implement recursion, and the operator we need is a reference. The reference will go and look up an expression in a table given the reference name. If we have this, then the expression can reference other expressions to create recursive regular expressions or context-free grammars. Okay, so here we take the derivative. We simply have to go and look up the expression and then take the derivative of the looked up expression. And the same goes for nullable. We simply look up the expression and then calculate nullable on the looked up expression. This is very simple and it works for our case and most cases. The case it doesn't work for is left recursion. Let's look at the starting rule of our Raga again. This rule has no left recursion and it will work without any problems given our current implementation. But we could have just as easily rewritten it in a left recursion style. These two rules will match the same Ragas, but the second one uses recursion instead of the star operator. And it uses recursion on the left side. This means when we calculate the derivative or nullability, we will immediately be forced to look up the rule again, which would then just result in us having to look up the rule again, over and over, resulting in an infinite loop. Luckily, a way has been figured out around this problem. It uses laziness, memoization, and a least fixed point to get around this to stop the infinite loop. I've attached a reference where you can read up a little bit more about it. I encourage you to go and check out the resources if you're interested to learn more about Ragas or how to solve the left recursion problem. In the next video, I will show you how to generate musical Ragas. I'll do this using the algorithm discussed in a digital audio workstation called Ableton Live with Max MSP and JavaScript.